Alright, so in this video I'm going to show how to use dependency injection as a kind of mechanism to provide tooling for AI CodeGen. Right, so we think of tooling in terms of tool that you provide to the models, and some of the other tools like web scraping or computer use. Here we're extending the idea to actual code generation, where we tell the AI to generate a certain type of code and then tells it that as part of that code it will use certain objects and what the interface that those objects expose. That way it can use the objects without worrying about how to actually create the objects. And then, when it comes time to actually run the code that the AI generates, we can inject the object itself. It's a nice way to do automation, lightweight automation. You create your tools, you can have a repository where you define the tools, and then you make it available for the AI. Here's an example of a tool that we have, which does it's a simple parser. It parses JavaScript and can parse Groovy code as well. Here's a project for that. It's just a standard project for our AI dev assistant. If you open this up, this is basically the object definition that would eventually get fed to the AI. It's a simple JSON manifest, describes what this tool does, provides some a general description, and then the methods that it exposes. And the idea is that in your prompt, the AI would use that information to determine first which tool to use, and then basically wrap a code around it. And here's the actual implementation. This can be installed as a system tool. Right now we're in a particular user directory, but it can be installed system-wide. That way, multiple users on the system can leverage the same tooling. Here's a reference that we have. This is how, or at least one way you can refer to a tool, right? To tell the software assistant to use a particular tool. So let's open up a session. We'll use a Gemini session. I'll clean this up. And we'll open up the software developer assistant. Alright, we'll do a two-use test. So this approach is only for Groovy, and it's only for Solvent specific code. The concept itself can apply to anything, any kind of software platform. You can implement the same approach in any other environment. For this environment, it's for Solvent code. Solvent code being, executables like this stuff. Right? It's written in Groovy. Frankly, it can be Java. Most of this stuff is Java. Groovy is a superset syntax of Java. You can look up the documentation if you want details on what all of that means. So we're gonna use a software assistant here. We tell it that it can use tools. If you don't specify a path here, it will attempt to use a tool registry. There is one configured, but it's not pointing to the right stuff, so it won't work. That's another way also to expose system-wide tools. So we drag and drop the tool reference here. We're basically saying use this tool, which is in the user's directory, and it will find it in there. Let's just increase the context here, just to be sure. And I think all of this looks good. Let me see which directory it points to. Here's a work working directory, so it's going to dump the code that it writes into this directory. So I could copy and paste the instruction here, but I'm actually going to speak it out. So we'll turn on speech, and then I'm going to follow on by actually saying what it should do. Write code that will implement a scanner. The scanner would expose a method that accepts a path for a given directory, and it will scan that directory for files that have extension .ste. Those files are Groovy files. It should parse the Groovy code in the file and return the result. Alright, so we just recorded our instruction. Now let's assume everything else is right here. Let me clean up the logger just in case something goes wrong. Alright, we'll issue that instruction and see what actually happens.
I've saved the code to /tools /CodeGen /scanner.st . The /scanner class in /tools .CodeGen has a method called /scandia . This method takes a directory path, scans it for /st files, parses the Groovy code in each file using the solvent code parser and returns a list of class node objects. Any parsing errors are logged.
Alright, so we have our scanner. It's been built, and we can take a look at the code. It recognizes from this tool object definition here what the object name should be, so it dutifully declared it. I made a mistake here. This is incorrect. Sometimes it gets it right, sometimes it doesn't, but it should basically be this, because this object is going to get injected into this code. And I see some other things in here. This should probably work. So it has a class node, which is available, should be available in class path, so we'll leave that as it is. Alright, so everything else looks good. Again, the gist of the idea here is that instead of, you're going to have a lot of use cases where you just want to implement a fairly simple automation around utilities that you already have, and those utilities in effect are your tools. The automation that you want to implement are specific use cases, so there are all kinds of variations that you can implement depending on the utility, abstracting the utility functionality in a way that the AI doesn't have to worry about doing that, where it can just wrap what is in essence boring logic around it, like it did here. can be very useful. There are plenty of use cases where you don't really want to have to spend a whole lot of time thinking about what needs to be done, and the AI can just spit out code that you know is going to work. All right, so we have this, and here's a driver, which is, again, auto-generated to do the injection. So here, we're leveraging some of the capabilities of the Solvent platform to initialize the tool utility object, and then we inject it here to invoke the scanner. Right? It does all of that automatically for you. For tooling, basically this object determines, it's how we define the entry point for the tool, and I believe it's what's referenced here as well. Alright, maybe some change has been made here. It really should be referenced in tool here, so that we have a standard way of, a standard entry point to, but this should work as well. Alright, so we have our tool reference here. It called the scan function that it generated. It provided the parameters here so we can supply this directly. So now we're going to scan, we'll actually scan the tool source directory and see what, get the full path here. This is the full file system path of that directory, and we'll run this. Alright, you might not see this screen, but it actually does come up in the browser. We can also run this internally. Let me see, test this. Let's do this. Run the test. Alright, we'll leave that as JSON. And just try simulation and see what it comes back with. Hopefully nothing broke. Let's see. Yeah, that did not. Let's see. Alright, so there are some issues with doing the simulation. Hold on to look into that. I'm sure I'm missing something there. In any case, it does run. You can't see the other tab, but if you run it directly from the browser, it runs. So that's, that's the gist of the idea here, is you get AI to do boring coding to reference your tools or utilities, and it's a very easy way to do lightweight automation. This is part of the functionality of the software dev assistant, which is an AI assistant that we have. It does the usual stuff, right? If I change, let's see, I add a function here and call it scan first file only. And then I think this looks good as it is. And then just hit go here. This is click and go there is tantamount to the tabbing stuff that everybody's doing with things like Cursor and similar IDEs or text editors. It should generate code, contextual code, and implement that function.
I saved the code to /CodeGen/scanner.st. No metadata generation is needed because I didn't add any new public methods.
Alright, so that's not what I wanted. Instead, what I want is this. We're going to turn on next code block prediction, and then turn on cursor mode. That's really what we wanted. And then I'm going to do what I did previously, which is scan dir first. So this time around, so we can reset the session when it runs with cursor mode enabled, basically behaving as it should. And then next code block, we're basically just telling it, given all the context, tell me what you think the next, the logical code block should be. So we'll hit go.
This method scans a directory for the first .st file and returns the parsing result. If no .st file is found or an error occurs during parsing, it returns null.
Turn off speech. Alright, so it did, it did the tab thing. It altered and returned the first one. It's kind of, I think the prompts still need to be tightened up. So here you saw that it generated the whole function. Sometimes it does that, sometimes it doesn't. It's not a big deal. You can remove it when it does. But we have the cursoring functionality, and we have the tool use. Tool use is very nice. Once you get a good collection of utilities, it's the kind of thing that can really help. With just simple tasks, there are all kinds of things that you want to do, and perhaps do repeatedly, that you don't want to have to think about. Maybe you work for a company that has, let's say, an API, and you help customers. Often it happens that you really want to help customers use automation and leverage the API, but every time you need to do even something simple, you have to go write code. In such a case, you could build up a nice repository of utilities, and then for every unique customer request, you just tell AI to write the boring code around your utilities, and you're good to go. All right, thank you very much.